Documentation is a description of what has been implemented based on the design and architectural requirements. Documentation should detail how something has been designed, architected, implemented without necessarily addressing the why aspects and the design requirement goals. Documentation in smart contract projects is typically in the form of README files in the GitHub repository describing individual contract functionality combined with the functional NAT spec and individual code comments. As discussed earlier, documentation in many cases serves as a substitute for missing specification and provides critical insights into the assumptions, requirements, and goals of the project team. Understanding the documentation before looking at the code helps auditors save a lot of time in inferring the architecture of the project, contract interactions, program constraints, asset flow, actors, threat model, and risk mitigation measures. Mismatches between the documentation and the code could indicate either stale or poor documentation, software defects, or security vulnerabilities. Therefore, given this critical role of documentation, the project team is highly encouraged to document thoroughly so that auditors do not need to waste their time inferring all the above aspects by reading code instead. Software testing or validation is a well-known fundamental software engineering primitive to determine if software produces expected outputs when executed with different chosen inputs. Smart contract testing has a similar motivation but is arguably more complicated despite the smaller sizes of smart contracts compared to Web 2 software. Smart contract development platforms are relatively new with different levels of support for testing, and projects in general have very little testing done at the audit stage. Testing integrations and composability with mainnet, contracts, and state is non-trivial. Test coverage and test cases give a good indication of project maturity and also provide valuable insights to auditors into assumptions and edge cases for vulnerability assessments. Therefore, auditors should expect a very high level of testing and test coverage because this is a must-have software engineering discipline, especially with smart contracts that are by design exposed to everyone on the blockchain and end up holding assets worth tens or hundreds of millions of dollars. And this quote from Dijkstra captures the role of software testing really well. He said, "Program testing can be used to show the presence of bugs, but never to show their absence." And this is similar in spirit to what we have discussed about security audits as well earlier. Let's now talk about static analysis. Static analysis is a technique of analyzing program properties without actually executing the program. This is in contrast to software testing, where programs are actually executed or run with different inputs to examine their behavior. And with smart contracts, static analysis can be performed on the Solidity code directly or on the EVM bytecode and is usually a combination of control flow and data flow analysis. Some of the widely used static analysis tools with smart contracts are Slither, which is a static analysis tool from Trail of Bits, and Maru, which is a static analysis tool from Consensus Diligence, both of which analyze intermediate representations derived from Solidity code of smart contracts. Fuzzing or fuzz testing is an automated software testing technique that involves providing invalid, unexpected, or random data as inputs to software. This is in contrast with software testing in general, where chosen and valid data is used for testing. So in fuzzing, These invalid, unexpected or random data are provided as inputs, and then the program is monitored for exceptions such as crashes, failing built-in code assertions, or potential memory leaks. Fuzzing is especially relevant to smart contracts because anyone can interact with them on the blockchain by providing random inputs without necessarily having a valid reason to do so or any expectation from such an interaction. This is in the context of arbitrary Byzantine behavior that we have discussed multiple times earlier. The widely used fuzzing tools for smart contracts are Echidna from Trail of Bits and Harvey from Consensus Diligence. Symbolic checking is a technique of checking for program correctness by using symbolic inputs to represent a set of states and transitions instead of using real inputs and enumerating all the individual states or transitions separately. The related concept of model checking or property checking is a technique for checking whether a finite state model of a system meets a given specification. And in order to solve such a problem algorithmically, both the model of the system and its specification are formulated in some precise mathematical language, and the problem itself is formulated as a task in logic with the goal of solving that formula. There is decades of research and development in this domain, and I would encourage anyone interested to explore the many references available here. For smart contracts, Manticore from Trail of Bits and Mithril from Consensus Diligence are two widely used symbolic checkers, which we will touch upon in later slides. Formal verification is the act of proving or disproving the correctness of algorithms underlying a system with respect to a certain formal specification or property using formal methods of mathematics. Formal verification is effective at detecting complex bugs, which are generally hard to detect manually or using simpler automated tools. Formal verification needs a specification of the program being verified and techniques to compare the specification with the actual implementation. Some of the tools in this space are Certora's Prover and Chain Security's Verx. KEVM from Runtime Verification is a formal verification framework that models EVM semantics. Manual analysis is complementary to automated analysis using tools. It serves a critical need in smart contract audits today. Automated analysis using tools is cheap because it typically uses open source software that is free to use. Automated analysis is also fast, deterministic, and scalable, but however, it's only as good as the properties it is made aware of, which is typically limited to those concerning solidity and EVM related constraints. Manual analysis with humans, on the other hand, is expensive, it's slow, it's non-deterministic, and it's not scalable because human expertise in smart contract security is a rare and expensive skill set today. And we are slower, prone to error, and also inconsistent. Manual analysis, however, is the only way today to infer and evaluate business logic and application level constraints, which is where a majority of the serious vulnerabilities are being found. Let's now talk about the concept of false positives and false negatives, which are really critical to understand in the context of smart contract audits or security in general. Compared to true positives, which are findings that are indeed vulnerabilities, false positives, on the other hand, are findings which flag the presence of vulnerabilities, but which in fact are not vulnerabilities. And such false positives could be due to incorrect assumptions or simplifications in analysis, which do not correctly consider all the factors required for the actual presence of vulnerabilities. False positives require further manual analysis on findings to investigate if they are indeed false positives or if they are true positives. And a high number of false positives increases the manual effort required in verification and also lowers the confidence in the accuracy of findings from the earlier automated analysis. On the flip side, true positives might sometimes be incorrectly classified as false positives, which leads to such findings and the vulnerabilities behind those findings being ignored, left behind in the code instead of being fixed, and may end up getting exploited later. On the other hand, false negatives are missed findings that should have indicated the presence of vulnerabilities, but which are in fact not reported at all. Such false negatives again could be due to incorrect assumptions or inaccuracies in analysis, which do not correctly consider the minimum factors required for the actual presence of vulnerabilities. False negatives, per definition, are not reported or even realized unless a different analysis reveals their presence or the vulnerabilities are realized only when they're exploited. A high number of false negatives lowers the confidence in the effectiveness of the earlier manual or automated analysis. Compared to this, true negatives are missed findings or findings that are analyzed and dismissed, which are in fact not vulnerabilities. So these concepts of true positives, false positives, true and false negatives come up often in smart contract auditing and in security in general, and therefore this terminology and the distinction between these types should be well understood. Let's now talk about audit firms. There are several teams or firms that have security expertise with smart contracts and Ethereum and provide auditing services. Some have a Web2 origin from the traditional audit space, where they provide other security services besides smart contract auditing, while some others are specialized specifically in smart contract audits. And there are a few others as well that are super specialized in certain formal verification, privacy, or cryptographic aspects within this space. There are at least 30 plus audit firms that are widely cited in this space, and this includes the Bootcamp partners, Consensus Diligence, Sigma Prime, and TrailorPins. Having discussed audit techniques at a high level, let's now talk a bit about the tooling that is used in this space. Smart contract security tools are critical in assisting both smart contract developers as well as auditors with detecting potentially exploitable vulnerabilities, highlighting dangerous programming styles, or surfacing common patterns of misuse. None of these, however, replace the need for manual review today to evaluate contract-specific business logic and other complex control flow, data flow, and value flow aspects. So these tools at best complement manual analysis today. We can think of tools in this space under different categories, such as tools for testing, test coverage, linting, static analysis, symbolic checking, fuzzing, formal verification, visualization, disassemblers, and finally monitoring and incident response tools. Let's now discuss some of the widely used tools in these categories. We will only dive into a few of them in some detail and only touch upon the others. Like I said earlier, I would really encourage you to explore these tools during this module. So install them. Most of them are open source and freely available. play around with their options to understand how they work, how effective they are, and how they would fit within your toolbox when you start auditing smart contracts. So let's start with Slither, which is a static analysis tool from TrailorBits and one of the most widely used tools in this space. Slither is a static analysis framework written in Python 3 for analyzing smart contracts written in Similarity. It runs a suite of vulnerability detectors, prints visual information about contract details, and also provides an API to easily write custom analysis. This helps developers and auditors find vulnerabilities, enhances their code comprehension, and also quickly prototype any custom analysis that they would like. It implements 75 plus detectors in the publicly available free version. And we'll cover these different aspects of Slither in the forthcoming slides. At a high level, Slither implements vulnerability detectors and contract information printers. It claims to have a low rate of false positives, and the runtime is typically less than 1 second per contract. It is designed to integrate into CI/CD frameworks. It implements built-in printers that quickly report crucial smart contract information and also supports a detector API to write custom analysis in Python. It uses an intermediate representation known as SLID-IR or Slither, as it may be pronounced, which enables simple and high precision analysis. As mentioned, Slither implements 75 plus detectors, each of which detects a particular type of vulnerability. Slither can run on Truffle, Embark, DApp, Etherline, or hard hat applications, or on a single Similarity file. And by default, Slither runs all its detectors. To run only selected detectors from within its suite, there is a detect option to specify the names of detectors to run. Similarly, to exclude certain detectors, one can use the exclude option to specify the names of detectors to exclude. Two specific examples of detectors are reentrancy ETH and unprotected upgrade. One can also exclude detectors based on the severity level associated with them. So for example, to exclude all those detectors that are classified as informational or low severity, one can use the exclude informational or exclude low options on this tool. One can list all available detectors using the list detectors option. So I would encourage you to take a look at this tool and the various options and configurations that it supports. Besides the detectors, like we mentioned, Slither has a concept of printers that allow printing different types of contract information using the print options. This helps in contract comprehension and gives us visibility into a lot of different aspects of the contract that's being analyzed. The various print options include things like the control flow graph, the call graph, the contract summary, data dependencies of variables, summary of the functions, inheritance relationships between contracts, modifiers, require and assert calls, and storage order of the state variables. And there are also many other details even from the Slither intermediate representation and at the EVM level. All these could be very helpful in quickly understanding the contract structure, getting a snapshot and zooming in on key aspects that are relevant from a security perspective. We've discussed in the security modules about how there are many security challenges with proxy-based upgradability. And a lot of them were inspired by checks implemented by Slither, along with documentation from OpenZeppelin on this topic. Slither has a specific tool called the Slither Check Upgradeability, which reviews contracts that use the delegate call proxy pattern to detect potential security issues with upgradability. These include initialized state variables, missing or extra state variables, and different state variable ordering between the proxy and implementation contracts, or different versions of the implementation contracts itself. This also includes missing initialize function that is present but that can be called multiple times because of the missing initializer modifier. And finally, function ID collision and shadow. All these upgradability aspects are conveniently packaged into a Slither tool, which makes it very handy for checking that aspect. Slither has a code similarity detector, which can be used to detect similar Similarity functions. This uses machine learning to detect similar and vulnerable Similarity functions. It uses a pre-trained model using Etherscan verified contracts that is generated from more than 60,000 smart contracts and more than 850,000 functions. This can be a useful tool to detect vulnerabilities from code clones, forks, or copies. Slither also has a contract flattening tool, Slither Flat, which produces a flattened versions of the code base, and it supports three strategies: most derived, one file, and local import. Most derived is for exporting all the most derived contracts. One file helps us export all the contracts in one standalone file. And finally, local import exports every contract in one separate file. This tool handles circular dependency and also supports many compilation platforms such as Truffle, Hardhat, Etherlime, and others. Slither also has a formatting tool, Slither Format, which automatically generates patches or fixes for a few of its detectors. The patches are compatible with Git. The detectors supported with this tool are a new state, SOLC version, pragma, naming convention, external function, constable, states, and constant function. The patches generated by this tool should be carefully reviewed before applying, just so that you're comfortable with what those patches look like and there are no bugs in it.